All right, got that going. Oh, I hope I didn't leave my book. There's like a 90% chance I left my book. Yeah, sorry about that. Thank you. All right, today we were starting with chapter 12, right?
Yes, sir.
Chapter 12, fortunately, it will be one of our easier chapters. It's just basically about arc lengths and angles. So we're finally going to get degrees like you guys have been wanting.
That's what a bunch of my questions are. Yes.
Okay, so let's see. Our first definition is giving us the definition of the arc. So if I have some circle, and I have pick 2 points on my circle, call it A and B. Here's A, here's B. Then we have this notion of the arc AB. What is the arc AB?
It's part of the circle between A and B.
It's a part of the circle between A and B. Very good, intuitive way to say it. So let's give our precise definition now. Create our central angle with those points.
Isn't there 2 arcs between A and B though?
Yes.
Good point. So we'll mention both those things in our definition. So the arc AB is all the points on the circle in the interior of the central angle, including the points A and B.
Say on the circle?
All the points on the circle in the interior of the central angle.
Okay, that makes sense. And you do that by a little stroke line on the top.
Yep. So remember, this is talking about this set of points. It's a geometric object. We'll talk about lengths of arcs later, and we don't have a good notation for that. I'll probably make up a notation because we have to talk about that. Anyways, so now, like Alan just said, sometimes we want to talk about the arc this way. When we want to do that, we pick some point exterior to the angle C, and then we say, let's look at the arc ACB. So you use 3 points with the point exterior when you want to talk about the arc going around this way, when you want to use the exterior of the central angle.
Why don't you just say, oh, that's the definition? Exterior.
Yeah. So when we're talking about this exterior arc, what is it? It's the circle intersected with the exterior of the central angle, together with the endpoints. And we typically symbolize it that way, using 3 points. When we're talking about the smaller one, we typically just use the 2 points.
So because if you did just 2 ABs, you'd have no idea.
If it's a straight angles don't have an interior, so you got to pick a side to make it clear. So when I have a straight angle A and B, A, B, I need to pick a C here, and so now I can talk about arc ACB.
Or ADB, if the D was on the other end.
Or if I put a D down here, ADB to talk about that way. Good. So, pretty simple definition. That's what we mean by the arc. Next one we've got talking about arc length. The length of one of these arcs. How do we talk about its length? Now, hopefully by now you are getting pretty comfortable with limits.
Yeah, I'm actually really comfortable and scared.
So here is how we calculate the arc length, which is the distance from A to B is one way to think about it. So first we take the line that goes directly from A to B, call that L1,
They split it in half.
calculate its length, so you get L1. And then we do it when we would have used 2 points, using 2, breaking this angle up into 2 equal pieces.
Half.
And so you would do, which give us L2. And I can break it up into 3 equal pieces.
And then 3 and 4.
And then 4, and then 5, break it up into n pieces. And so when you break it up into n pieces, like the dots I have, the more pieces you use, the better approximation it is. If I connect all those dots, we know how to calculate the lengths of segments. Add up the lengths of all those segments, gives you the arc length. Okay,
So you gotta choose a segment, because there's infinite.
there's infinite. Right, so when we talk about arc length now, so let's see, we'll do AB, we're talking about that thing's length. How should we specify its length?
Equals.
Should we put a line above it like that as well? That's what we mean by the length of the arc. Put an extra line above it.
Is that straight up?
Huh?
Okay, great.
Just a line above it. The same way that when we talked about the segment, we put a line above it to talk about its length, right?
So
Yeah, that's a line segment, that's the length of it.
That's the length of the line segment.
Yeah.
Okay, so I'll use a line above it for the arc length.
Yeah.
We'll just use that notation. Your author doesn't use that notation, making it up right now.
Okay.
By definition, we define the arc length to be the limit, as n goes to infinity, of this sequence, L sub n. Make sense? Very similar to how we define circumference.
So if I ask what the length of the limit is with the radii of 5 inches and an angle of 45 degrees.
Then how would you calculate that arc length?
Yeah.
We'll get to that. We'll give you some basic formulas you can use to go back and forth between these. Okay, theorem 1. If in a circle two central angles are congruent, they subtend arcs of equal length. Okay. So what's this saying? So I've got, maybe we'll piggyback on this picture here. So I've got one central angle. I'm going to draw another central angle. This isn't necessarily meant to be a straight line. Just two central angles in the same circle. And all I know about these two central angles is that they're congruent. I know that this angle is congruent to this angle. What am I trying to show?
The arc length is the same.
That the arc length is the same. I'm trying to show that the arc length of AB is equal to the arc length of CD.
Yeah.
That's what we're trying to show.
Okay.
You with me?
Yeah.
Okay. Now, I'll use primes to talk about the length down here and just L's to talk about the length up here. So L1 is what comes across like this. That would be L1, and L1 prime is going to be this length right here. You with me?
Okay.
How does L1 compare to L1 prime?
They're the same.
How do you know?
Because they have equal arc lengths.
Similar triangle.
We're
Those are
arguing
similar
though.
triangles.
They're not similar triangles, they're congruent triangles. They are similar, but they're more than similar, they're congruent. How do I know they're congruent?
Because they're
Angles. Base angles of.
Well,
Come on.
Because they have the same radius. It's side angle.
There you go, side angle side. This is the radius of the circle.
Oh yeah.
By side angle side, these two triangles are congruent.
Right.
So I know that L1 is equal to L1 prime, right?
Yes.
Similarly, what if I broke this into two pieces?
Then yes, because it's supposed to. If you divide.
So if I broke this into two pieces, pictures lie. If we broke that into two pieces, sorry,
You could do it like that.
this bisects the angle, so that angle is the same because that angle is the same because that angle, right?
Right.
This once again is a radius, this once again is a radius. And so by side angle side, this is congruent to that, this is congruent to that, they're all congruent to each other. We're good. And so, L2 is this length plus this length, L2 prime is this length plus this length. And so I know that L2 is equal to L2 prime. And similarly, L3 is equal to L3 prime, da 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 da.
Right.
And so finally, putting this all together, I know that
Length of AB.
the length of arc AB, by definition, is equal to the limit. I'm going to stop doing as n goes to infinity. Our limit will always be as n goes to infinity in this class. The limit of L sub n, which L sub n is the same thing as L sub n prime. That's what we're showing over here. L1 is equal to L1 prime, L2 is equal to L2 prime, dot, dot, dot.
Which is equal.
L
to,
sub n is equal to L sub n prime.
Right. Which
And
is-
so
in
I
that
can
equation,
substitute equals for equals,
Which is equal to the length of arc CD.
which is exactly what we mean by CD's arc length.
Right.
Make sense?
Yeah.
Anything weird there?
No.
Okay. Moving on to the next here. Let P sub n be any sequence of polygonal paths inscribed in the arc AB of a circle. And let LM be the sequences of lengths of these polygonal paths. Let SM be the lengths of the longest side of the path. Okay. Theorem 12.2, he doesn't give a proof here. There's a reason he doesn't give a proof here. It would be a very hard proof to give. But what he's saying is, when we're talking about the arc length, so when I was talking about the arc length of this, sorry, way missed the center of the circle. When I was talking about the arc length, first I split this into one even piece, and then 2 even pieces, and then 3 even pieces, and then 4 even pieces, dot, dot, dot. And I kept using even-sized pieces. You with me?
Yeah.
It turns out you don't have to use evenly sized pieces. All that matters is that all the pieces are getting arbitrarily small.
One more time.
Okay, so we did it by dividing this up perfectly. Imagine I didn't. Imagine instead I said, we're going to divide this up into 2/3, 1/3 down here.
Okay.
And then after that, I'm going to divide this each piece up into 2/3, 1/3. So I split this one up like this, and I split this one up like this. And then I go through and I divide each of the pieces again into 2/3, 1/3.
Right.
It would still, in the limit, give me arbitrarily small lengths, and so it gives me the same limit, still gives me the arc length.
Right.
Yeah, since each of the pieces still gets arbitrarily small, my calculation for the arc length still gets arbitrarily good.
Right.
And so you don't have to divide it up into perfectly even-sized pieces. All that really matters is your pieces are consistently getting smaller.
Does it matter that they're proportional?
No.
So I'm saying it doesn't have to be 2/3.
Yeah, so I divide up into 2/3, 1/3 one time. Next time I can split it 50-50. Next time I can split it 1/5, 5/5. Next time I can split it 99-1. And I can change my ratio left and right. All that matters is I'm consistently making all those pieces arbitrarily small. Since every piece gets arbitrarily small, then that works. That's kind of a more advanced theorem from real analysis. It's kind of a hard one to prove. So he wanted to just point that out. We're not actually going to prove that. Okay, next. Easier to show the picture first and then say it. So let's get our picture up. So drawing our circle, and this time we have A, B, C, trying to make those look like very different angles. The next thing we want to prove is that the length of arc AB plus the length of arc BC is equal to the length of arc AC.
Easy.
You with me?
Yeah.
Okay. Now, what I'm going to do is I'm going to split this one up into polygonal paths. I'm just going to evenly split it each time. So we split it up like that, and this one we split up like this, right?
Right.
So up here, the one I just drew, I'm going to signify with L2. The one over here, I'm going to signify with L2 prime. So I'll use regular L's to talk about the lengths that we divide this up into, and primes for this one. Here's when it's 2. Divide up into 10, divide up into 50, divide up into 100. And so in general, if I have this divided up into a bunch of pieces, so I divide this up, and this up into pieces. This one's pieces will be slightly bigger if I split them up the same amount of times, right?
Right.
But either way, I'm marking L sub n up here and L sub n prime down here. With me?
Yes.
Okay, so go ahead.
What you're saying is how you're measuring that length is by your, what should I call them, your straight line?
Yeah, these segments. Remember, segments are straight.
Segments, yeah.
Right, so I break it up into n segments and calculate the length of each of those n segments and add it up.
To get a rough estimate, right?
To get an approximation for the arc length AB. By definition, the arc length AB is what you get in the limit. If I broke this up an infinite number of times,
Your limit, yeah.
then you perfectly calculate that arc length. By definition. That's what the arc length is.
But let's say we were working with numbers.
So let's say that you had an actual real world problem that you were trying to solve. and you were trying, well, in that case, you just use a formula. We'll work up to a formula that you'll see how to use. Okay, but anyway, so we all understand the problem and what my notation is here?
Yes.
Okay, so tell me, what is arc AB's length?
It's the limit of Ln.
Perfect. This is the limit of Ln. As n goes to infinity, told you I'm not writing that anymore.
Right.
And we're trying to add that with what?
Limit of Ln.
The limit of L prime. as it
The
goes-
limit of Ln prime. Perfect.
Ln prime goes to.
Now you might remember last time we proved that the sum of the limits is equal to the limit of the sum.
Yeah.
So I showed you that if the limit of an is equal to a and the limit of bn is equal to b.
Oh, then
Oh,
a
yeah.
plus, then the limit of those two equals a plus b.
Perfect. So same thing here. The sum of the limits is equal to the limit of the sum. You with me?
Yeah.
Now, what is Ln plus Ln prime?
AC.
It's AC.
Right, it is a length of a polygonal path from A to C. The only weird thing about this is we divide this one into slightly bigger pieces than we divide this one into.
Right.
Our previous theorem says that doesn't matter.
Right.
So that's why he quickly drew in the previous theorem so that we can use this one. So previous theorem says that doesn't matter. This is still a valid way to calculate the limit. And so this is, by definition, the arc length of AC. Sorry, this was equal to AB. Probably should have done that all in one line. Those two are equal to those. Add them together, gives you that.
Right.
So this proof pretty much reduces to the fact that the sum of the limits is equal to the limit of the sum.
Yeah.
Okay. Keep thinking my book's on there. All right. So that was theorem 12.3. Theorem 12.4. If in a circle one central angle is greater than another central angle, the greater angle subtends the longer arc. Okay. So we already proved that if two central angles are identical, if two central angles are congruent, their arc lengths are congruent. We already proved that.
Right.
Now I need to prove that if I've got some circle here, AB, that's not necessarily a right angle. Just need to draw it so it's obviously bigger than this one. And here's CD. So I know that AB is a larger angle than CD. I need to prove that the arc length of AB is greater than the arc length of CD. How am I going to prove that? What do I know I can do if I've got one angle is bigger than another?
You can put it inside of it.
You can put it inside of it. So I know that there must exist some ray, C prime, such that this angle is congruent to this angle.
Yeah.
Right?
Right.
And now what do I know?
There's that which means it's bigger.
Perfect. So I can say that the arc length of BC prime is
It's equal to the arc length of CD prime.
is
A BC prime.
maybe let's label some arc length so that we don't have to say this same thing over and over again. I'll call this arc length here L, and I'll call this arc length here L prime. You with me?
Yeah.
What do you call him?
Well, so now I know that AB's arc length is equal to L plus L prime, which is greater than just L by itself, which is equal to the arc length of C prime B, which is equal to the arc length of CD.
Oh, that's pretty snazzy. You did there.
Did all that right?
Yep.
So CD's arc length is less than AB's.
Right.
Follow each piece of logic there?
Is
Nothing
less than?
Yeah. I was showing that probably should have flipped the way I wrote this. I'm showing AB's arc length is
Oh.
greater than CD's.
Oh, yeah.
Maybe that's a better way to read that.
I thought.
Yeah, should have said that. Good?
Yeah.
Okay. Corollary of this. if one arc of a circle is longer than a second arc of the circle, the longer arc subtends a greater angle. Okay, so now we want to do the converse. What we show here is that the one with the bigger angle, I showed that the one with the bigger angle here had the bigger arc length.
Oh, show the bigger
Now we
arc
need to go
length.
the other way. We need to show bigger arc length means bigger angle. So let's show the converse of that. Draw our picture here.
So what you're trying to prove is your arc length is based on your angle. Your angle.
Yeah, that there's this correlation that the bigger the angle, the bigger the arc length. So I've got AB, I've got CD.
Is that meant to be 90 degrees?
No, just an angle. But what I know is that the arc of AB is bigger than the arc of CD. I'm trying to argue that this angle is bigger than this angle.
Yeah.
You with me?
Yeah.
So let's write this one out more fully. So 1, let AB have an arc length greater than arc length of CD. Okay, I'm trying to argue that AB's angle is greater than CD's. Comma, I'm just going to label some stuff. And let alpha equal angle AOB. O we typically always use as the center of the circle. And
Does that stand for something?
Beta origin equals COD.
Same.
All for origin.
Origin.
Okay, so I'm just labeling this angle right here alpha and this angle beta so that I can keep making reference to them.
Right.
Good?
Good.
Okay, I'm trying to argue that alpha is bigger than beta. All right, 2. Assume by way of contradiction that alpha is not greater than beta. If alpha is not greater than beta, what are our options?
Then alpha, then beta, alpha can fit into beta.
Well, just what exactly do you know? If I tell you that x is not greater than y, what do you know?
Y is greater than x.
Or
They're the same size.
they're the same. This is the same information as x is less than or equal to y. So if alpha is not bigger than beta, then either alpha is congruent to beta or
They're the same size.
they're the same size. Or
Or they're bigger.
alpha is smaller than beta. Yeah.
Sorry.
So this gives me alpha is congruent to beta or alpha is less than beta. Let me show in either case we get a contradiction.
Right.
3. If alpha is congruent to beta, what do I know?
The same radius.
If alpha and beta are congruent, it was our first theorem, then their arc lengths are congruent.
Right.
So if alpha is congruent to beta, that gives me AB's arc length is equal to CD's arc length. Contradiction. Because we said let AB be greater than CD.
Yeah.
Okay, 4. If alpha is less than beta, that gives us from our previous theorem
It can fit inside.
that the smaller angle has a smaller arc length.
Right.
So that gives me that if alpha is smaller than beta, then that gives me that arc length, the arc length of AB is less than the arc length of CD. Contradiction. Therefore, alpha must be greater than beta. So that's how we prove that one.
Pretty straight up.
Good?
Yeah.
All right. Next one. 2 central angles of a circle are congruent if and only if they subtend arcs of equal length. Okay. So this is theorem, I think it's 12.6. 12.6. This one we kind of need to write out so that you can see it. Let's do it with our picture here. It's saying that Maybe I don't need to write out this whole proof. It's pretty much as simple as this one up here. So this one is saying that if I have two arcs, A, B, C, D. We'll label the angles the same way I did before, alpha, beta. It's essentially saying that alpha is congruent to beta if and only if AB's arc length is equal to CD's arc length. So I need to show if this is the case and this is the case, and if this is the case and this is the case.
Right.
Now, our first theorem that we proved was showing this way. It was showing if the angles are congruent, then the arc lengths are congruent.
Right.
So going this way was given by theorem 1.
So isn't it kind of the converse of that?
No.
Well, it's saying the same thing, just
It's very similar.
alpha and beta are switched.
No, up here we were doing if one's less than the other, then the other's less than the other.
Oh.
Here we're doing
Oh, you didn't already prove that if alpha and beta are the same, or if if the arc length of AB is congruent or equal to the arc length of CD, then alpha and beta are congruent. You didn't say
we didn't prove that one yet. So we proved this way, that was our first theorem, 12.1. We still need to prove this way. How do we prove this way? It would be same thing we did up here. Assume by way of contradiction it's not the case, and you'll get a contradiction.
Right.
So going this way, we would say assume by way of contradiction. Assume by way of contradiction that, I don't know why I did capital T there, that AB is equal to CD and alpha is not congruent to beta. So if alpha is not congruent to beta, what do we get? We either have alpha is greater than beta,
Alpha is greater or
or alpha is less than beta. Right? It has to be one of those three.
Right, yeah.
If alpha is greater than beta, what does that give me? That gives me the arc length of AB is greater than the arc length of CD.
Contradiction.
Contradiction. If alpha is less than beta, what does that give me?
The arc length of AB is less than the arc length of CD. Contradiction.
Get my sloppy. And so there you have it. Therefore, they have to be congruent. All right. Theorem 12.7. If arc AB and arc A prime B prime are arcs on two circles of radii r and r prime respectively, and are subtended by congruent angles, then the arc lengths are proportional to the radii. Okay. So here's what this is saying. So we've got two circles, one bigger, one smaller.
Okay.
On this circle, we've got some angle with points A, B, and we have its arc. Here, we've got some central angle terminating in the points A prime, B prime. What we know is that this angle is congruent to this angle.
Okay.
We're trying to show that this arc length is proportional to this arc length.
Proportional, not equal.
This arc length to its radius is proportional to this arc length to its radius. That's a fair way to say it. So this one we're going to say has radius r, this one we're going to say has r prime. So what am I trying to show?
The angles are congruent, right?
I'm trying to show that AB's arc length over A prime B prime's arc length is equal to r over r prime. They're proportional. I know that the angles are congruent. That's given information. Here's what I'm trying to show.
Right.
Okay.
Wait, the angles are proportional, not the arc length.
I'm trying to show that the arc lengths are proportional to the radius
Right.
if the angles are congruent. Okay, so first thing to notice, if I split this up, AB, if I divide that side into one segment and I divide that side into one segment, looking at,
They're similar triangles.
they're similar triangles. How do you know?
Because the radius, they're both.
It's not the radius in this case because they have completely different radii. How do I know that these two triangles are similar?
Angles. It's gotta be angles, right?
That angle is the same as that angle. Okay, I know that. How am I going to argue that this angle is the same as this angle and this angle is the same as this angle?
It's equilateral.
No, my picture just makes it look that way. I could have picked a smaller slice.
Oh, thank you. Right.
So A and B are just 2 points on a circle. It's not equilateral, but what is it?
Similar.
Just look at this triangle for a second. Forget this one. What do you know about this triangle? It's isosceles.
Right.
So I know that this side is congruent to this side. So what do I know about its base angles?
They're congruent.
They're congruent. So whatever this angle is, it has to be congruent to whatever this angle is.
Right.
Okay. This is also an isosceles triangle. And I know that this angle is the same big as this angle. And I know that this sums to 180, the same way that this sums to 180.
And those two are congruent. Therefore,
Right.
A and B, you have to equal A prime and B prime.
So that angle has to be the same as that angle.
Therefore, they're similar.
Everyone see that? Okay. So I know that these triangles are similar. What do we know about similar
Their
triangles?
sides are proportional.
All their sides are proportional. So if I was calling this side here L1, and I was calling this side here L1 prime,
Those are proportional to each other.
then I know that R over R prime is equal to L1 over L1 prime. That one is supposed to be down there. Okay, what if I were to divide each of these up into two pieces instead?
Then it's the same thing. It's
Same argument.
Yeah. You just have to add.
You just take it one triangle at a time.
Right. Because then now you have two isosceles instead of just one.
That triangle's isosceles, that triangle's isosceles, that triangle's isosceles, that triangle's isosceles. That bisects, so that angle's the same as that angle's the same as that angle. And we have, all the triangles are similar. And so, these ratios are still going to be similar, so this is going to be the same thing as L2 over L2 prime.
Right.
Is equal to dot dot dot. In general, it's going to be equal to Ln over Ln prime. You follow everything up to there?
Yeah.
Anything weird? Okay. So now,
So it's just proving.
here's what we're trying to prove. Go to the side over here. Trying to show that the length of AB over the length of AB primes, arcs, is equal to R over R prime. So now let's prove
Okay.
that. So,
Don't you have to prove that the radius, the arc length is determined by the radius?
no, we're just showing it's proportional to the radius. In a way, you could say that showing it is determined by the radius. In other words, the bigger the radius, the bigger the arc length, is what we're showing.
Right.
Okay, so now, the arc length of AB over the arc length of AB prime is, by definition, the limit of Ln over the limit
Ln prime.
of Ln prime. Wrong up. Ln prime. Now, this isn't one that we proved for you, it's one that we told you, one of these limit rules. But the limit of the quotient is the quotient of the limits,
Right.
as long as the bottom is never 0. We have no notion of 0 length, so the bottom isn't 0. So this is equal to the limit. Well, we have a notion of 0 length, we don't have a notion of negative length, but our length is never 0, assuming we have some angle.
Right.
So this is the limit of, oops, that's quickly. This is the limit of Ln. I don't know what's going on in my brain. Keep wanting to do those L's. Ln over Ln prime. Right? Now, ln over ln prime, we know is equal to what?
B over A, the arc AB equals.
No, that's what the limit of ln is, the arc length of AB. But what about ln just by itself?
Yeah.
What do I know ln over ln prime is? Always and forever. Replace it with any number. 1 over 1, 2 over 2, 3 over 3. What does this ratio always equal?
R over 1.
R over R prime.
R over R prime.
We showed R over R prime is equal to L1 over L1 prime, and L2 over L2 prime, and L3 over L3 prime, dot, dot, dot. So this is always equal to R over R prime. R is a constant, R prime is a constant over a constant is a constant. What's the limit of a constant?
Constant.
That constant. If I say, let's look at the sequence, 2, 2, 2, 2, 2, 2, dot, 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 what does that converge to?
2.
2. Same thing here, it's the same number over and over again. So its limit is just R over R prime. And there you have it. That arc length is equal to R over R prime. Good? Alright, next one. Suppose that L is a positive number less than or equal to 1/4 the circumference of a circle of a radius. Then there exists an arc of the circle whose length is that. Yeah, you can't really prove that good. So here's another one that we're not going to go over a proof for. We're just going to assume it. Here's what it's going to be. It's going to be pick any length L between 0 and the circumference of the circle.
Okay, there's an arc on that circle for it.
Then there is an arc on that circle that gives you that length. It's kind of like our completeness theorem that we used way, way back. This comes from our completeness postulate. Our completeness postulate was basically pick a segment, it always has some length.
What do you mean?
So that was one of our postulates way back.
Okay.
Pick a segment, any segment. So I've picked my unit, here's my unit, 1 foot or whatever.
Right.
Any segment you choose has a length. That's not something we proved, that's something we assumed.
Okay. Right.
So this is a similar thing for it. It's pick any arc you want on the circle AB, and it has a length. You would prove this from this, but it's a messy proof.
Right.
Okay, so that's one that we're going to assume. We're not going to prove. Now we get to, so that was theorem 12-8. Now we get to degrees. I think. Definition 12-3. On a circle of radius r, an arc length of 1/360th times 2 pi r is subtended by a central angle of 1 degree. Okay, so yeah, we're basically getting into our definition of a degree. Did we already talk about why 60s and why?
Kinda. It's because I
Kinda.
put the Romans.
So, no, I think it's Babylonians or Sumerians, some group like that. They used a base 60 counting system.
We use 10s, they use 60s.
Yeah, where we use 10s, they use 60s. Now, why did they use 60s?
Because
Well,
It's not the sun, right?
yeah.
so when I ask you to do arithmetic, so we use a base 10 system. When I ask you to do arithmetic, there's numbers that it's real easy for you to work with.
Right.
And those numbers are 1, 2, 5, and 10. It's real easy for you to do arithmetic with these numbers in your head.
Right.
If I say 40 divided by 2, that's real easy for you to do,
20.
right? If I were to say 2 times 5 times 10, that's real easy for you to do.
100. Right.
So anything dealing with doing arithmetic with these numbers is really nice, and it's because they go into 10 evenly. And so we can think about 10 and factors of 10 real easily in our head when we do mental math. They use a base 60 system. What does this factor into? This factors into 1, 2, 3, 4, 5, 6. And then
30.
8,
10.
9 also goes into it, right? No.
10 does. 9 does not.
8 also doesn't, sorry. 6, not 7, not 8, not 9, but then 10. And then 12. And that's enough of it. But the point is, all these early numbers go into 60 real nicely. And so it's real easy to think, made it real easy to do mental arithmetic working with these common numbers that would come up over and over again. That's the speculation.
That's the reason we think they chose 60.
Yeah, they did use a base 60 counting system. That much is clear. Here's the reason that we think that they did it, is because it's a very divisible number. Real easy to do arithmetic with. And so since these were the people who did a lot of the early measurings of time, all of our time is done in terms of base 60 systems. So we have 60 seconds in a minute, 60 minutes in an hour, and we also take a circle and we divide it up into 360 degrees. Completely arbitrary. Why did they do that? Probably something with their calendar and the fact that they thought that there were 360 days in a year.
Which there is.
365. So 365 and a quarter is a little better. Get into the Julian calendar. 365 and a quarter with some other stuff that we leap years and all that stuff gets you to the Gregorian calendar. So there were some leaps there, but the point is they were one of these early people to do it. So why do we divide a circle up into 360 degrees? It is super arbitrary.
But super
Nothing special about it.
Super easy to talk about 60.
Well, they did it in base 60. If we were to redo this today, it would make a lot more sense to divide it up into 100 segments or something like that. But we adopt whatever the notation was, and so we divide 1/360th of the circle up, we call 1 degree. The more precise definition is take 1/360th of the circle. Take that arc length that is 1/360th of the circle. The corresponding central angle is 1 degree.
Right.
You with me?
Yeah.
So, we'll say this one more time. What would this length right here be in terms of the circumference?
Be the
300. So imagine I start here and you tell me walk 1 degree. So I walk from here to here. So at the central angle I walked is 1 degree. How far did I walk?
1/360th.
I walked 1/360th of the circumference.
Right.
Right?
Yeah.
If you know the radius of your circle, then you might rewrite that as I walked 1/360th of 2 pi r. Right? That's your circumference.
Yeah, okay.
You with me?
Yes.
So that's the definition of 1 degree. It's the central angle whose arc subtends 1/360th of the circle.
You're saying this is how the Romans would say 1 degree?
This is the definition of 1 degree. 1/360th of the circle. 1/360th of the circle. That's what we mean.
Right.
Yeah.
Okay. So now you're asking questions like, okay, I've got some angle here in degrees, some angle theta. How do I figure out its corresponding length, L?
How many degrees is it?
Okay, we'll do a concrete case and then we'll get more general after that. So let's say that this right here was 30 degrees. How do I figure out L?
It's 30th. 3/60th. It's
30,
360.
2 pi r.
So P pi.
So tell me what to write.
3360
One over
is
12.
30/360ths
Time the 2
of
times 2 pi r. Perfect. And that gives you the corresponding length. In
That's
general, if I would have given you theta here, then you could have plugged in theta here.
Right.
And what most formulas will do when you see them is they'll cancel out 360 and 2 here. Because 360 goes into 2, or 2 goes into 360
Wait,
180
why
times.
theta there?
Huh?
You called that theta?
Yeah, because now we don't know the angle. When it was 30, we did 30. If theta was 20 degrees, we put 20. Theta is a standard variable for representing an angle.
We don't know what theta is. That's
It's a variable. The same way when I say
X.
y is equal to 2x plus 1, and you say, what's x? It's a variable.
Yeah.
Theta is a variable. Based on theta, this gives you the length. Based on x, that gives you the y. So the length is equal to theta divided by 360, where theta is your angle, times 2 pi. Cancel the 2 and the 360 out, and the way it's typically written is theta is equal to 2 pi, pi r over 180. And so that's the common formula that you use. So if your problem asks you, it says you're on a circle, the radius is 10 meters or whatever, and the central angle is 37 degrees, what's the length? Here's a formula you use. You'll also be told to do the inverse of this, where you're given the length and you need to find the angle. So one formula you have is length is equal to the angle times pi r over 180. If you need to do the reciprocal, then you would say theta is equal to, and we need to just multiply both sides by the reciprocal of this. So it's going to be equal to L times 180 over pi r. You see that?
Yeah.
So those are your two basic formulas for going from an angle to an arc length, and from an arc length to an angle using degrees. Okay, he uses L for length and capital M for, I guess, a measure of the angle, but same formula. Okay. If two angles are congruent, they have equal measures. It's going to be a similar argument. We won't prove that one. So, from now on out, here's something we're going to assume. Something you've probably already been assuming. If two angles are congruent, they have the same degree measure. If two angles are congruent, they have the same degree measure.
Right.
Isn't the degree measure the arc?
Since the degree measure is a function of the arc length, then you see how, since our arc lengths are the same, their degree measure has to be the same.
So, yeah, because we are proving.
Correct. Okay. So now, we're going to get to the non-insane way to talk about angles. Because breaking this up into 360 degrees, the fact that some ancient people did that, is super arbitrary and is a terrible way to measure angles. So we're going to introduce a far superior way to talk about angles and the measurement of angles, and it's called radians. Now, what was a degree by definition? We'll keep those formulas there. What was a degree by definition?
A degree by definition is
1/360th, right?
A degree by definition is 1 over 362 pi r.
No.
Oh,
Degree, 1 degree by definition
That's the length of the
Is
arc.
1
of
over
1 degree.
360.
is the central angle for 1/360th of a circle. Right?
Right.
why do they use 1?
Well, that's just 1 degree. And so if you want to talk about 20 degrees, it's 20 of those.
Oh.
That's just the definition of 1 degree. Now, far superior definition. Rather than marking off 1/360th of the circle, what if instead we mark off 1 radius of the circle? So pick the angle whose arc length is the same as the radius.
0.
What?
The arc length is the same. Oh.
Here's an angle, and its arc length is the same as the radius.
Okay.
Whoa.
That's a very nice angle, right?
No.
No?
Seems like it'd be a really hard angle, wouldn't it?
Well, by definition, this angle we call 1 radian.
Oh.
Rather than
That is nice.
Rather than measuring based off of 1/360th of the circle, we're going to start by measuring based off of 1 radius of the circle. So 1 radian gets you that far around the circle.
So what's 1 radian is? Radians are dependent on the size of the circle.
No,
Yeah, because it's.
because the circle grows proportional to its radius. If I were to draw a small circle, here's its
So
radius.
you can do a formula of degree equals how many radians.
Yes. 1 degree is roughly, I can't remember what it is, 58 point something degrees. But yeah, if I did a small circle, take its radius, mark it off, there's the angle,
It'd be the
whose arc
exact
length
same
is 1
angle. It'd
radius.
be the exact same angle.
Yes,
as
1
that.
radian, 1 radian. Same thing.
Okay.
Okay, so really quick, let's get comfortable with this. 1 radian gets me this far around the circle. Right? 2 radiuses gets me this far around the circle, so here's an angle of 2 radians. Right?
Yep.
3 radians will get me roughly this far around the circle. How many radians get me all the way around the circle?
6.28.
Don't approximate. How many radians get me around the circle? Precisely.
6.
Huh?
6 radians.
We don't
Well,
know.
exactly.
That's just what it looks like.
What is the distance from here going all the way around back to here?
Circle. It's pi r squared.
360 degrees.
Pi r.
No, what
times
is
two.
the arc length?
Pi r times 2.
It's the circumference.
Right, which is pi r times 2.
So it's 2 pi r.
Pi r. Yeah.
So
that
how many
radians-
radiuses does it take me to get all the way around the circle?
2 pi.
2 pi. So how many radians are in a circle?
2 pi.
2 pi. So let's go over this. If I go, so I start right here and I go all the way around. That's 360 degrees. How many radians is that?
2 pi r.
2 pi.
Pi.
Right?
Right.
What if I only went halfway around the circle? That's 180 degrees.
Pi.
Over here, it's pi. It's half of that.
This is how you get your unit circle.
Yeah, this is the start of the unit circle. We'll fill out the unit circle. What about 1/4 the circle? 90 degrees is 1/4 of that.
1/2 pi.
Pi halves. What about 60 degrees? What portion of a circle is 60 degrees?
Pi 1/3.
1/6.
It's 1/6 the circle.
So it's
Oh, yeah.
pi 1/3.
So pi thirds.
Yeah.
What about 45 degrees?
Pi 4ths.
Pi fourths. What about 270 degrees?
Pi 6.
No.
Pi.
No. It'd be right around 1.5 pi. No. Yeah. 1.5.
1.5 pi or 3 pi halves. Keep it in fractions rather than
Decimals.
decimals. So these are radians rather than degrees. They're far superior. I know that it'll take you some convincing of that, but once you get used to them, you'll realize that they're far superior. Why are they far superior? Let's say that I told you that someone started here and they walked around the circle. We'll say the circle has 7 meters radius.
So what you're saying is it takes 3.14159
Radiuses.
radiuses to get 180
Degrees.
degrees.
Oh, well,
Gets half the
pi
circle.
radiuses. So 1 radius will get you this far around. 2 radiuses will get you this far around. 3 radiuses will get you this far around. 3.14159 radiuses will get you exactly halfway around the circle.
Okay.
So it's in terms of radiuses. So now here's a simple question. So I start here and I walk until I'm right here. You know that I went 135 degrees around the circle. Question, how far did I go around the circle?
135.
You
Pi.
went to
What's the actual number of meters I walked around the circle?
A second. Pi squared, so it'd be.
And so you're going to have to plug 135 degrees into here and start doing your arithmetic to figure this out.
Right.
Right? Now, let's reset the scenario. And instead of telling you that I went 135 degrees, let's really quick think about that in radians. Just as a good exercise for you. You'll get used to think about radians better as time goes on. But that's 135 degrees in terms of radians.
It's in terms of radians. It's just
it's this 3 times,
Yeah.
right? 45, 90, 135. So it's 3 of these, so it's 3 pi fourths. If I would have given you this angle as 3 pi fourths in radians, and then I asked you to calculate the arc length around here, what's the arc length?
The arc length is the
If it's this many radians, that means it takes that many radiuses to get around that arc.
So 3 pi.
So it's
3 pi
just
fourths times
21 pi over 4. It's just the angle times your radius. And so the formula over here is this, but by definition, our arc length over here is just theta times r. Your arc length is equal to how many radians times your radius. And that's what a radian is. It's how many radiuses you need to get that arc length. And similarly, if you're just solving for theta, theta is equal to L divided by R. And notice how much simpler those equations are than these equations. That's why radians are vastly superior, and that's why you almost exclusively use radians as you get in more advanced maths. And you stop using degrees. It makes no sense. So we keep degrees for traditional reasons, but outside that, they're pretty useless. You with me?
Yes.
Okay, so with that, let's really quick start filling out a unit circle. Just plugging in the angles. What do we mean by a unit circle, by the way?
This is the measures of angles by in radians.
Well, why is it called a unit circle?
I actually don't know.
Because its radius is 1 unit. It's a circle with radius 1. That's why it's called a unit circle. Okay, so we're going to go around and we're going to mark these points. Well, we're going to mark the angles. And I want to talk about the angles in terms of degrees and radians. So how many degrees to get to this point on the circle?
1. No.
0.
0 degrees, or we could have said 360.
Yeah.
In terms of radians, it's going to be 0 or
2 pi.
2 pi. Perfect. All right, let's go straight up here. In terms of degrees, what is this?
90.
90. In terms of
5
radians?
halves.
Pi halves. All right, coming all the way around over here,
180
it's 180
or pi.
or pi. Coming down,
It's 90.
It's pi fourths.
It's
No, it's
200.
3 pi halves.
270 first, right? 90, 180, 270,
3 pi halves.
3 pi halves. Right, going from here to here, pi halves, 2 pi halves, 3 pi halves.
1. Why don't you just say 1 and 1/2 pi?
This is the way it's written. So getting you used to
Just
standard
like that,
notation.
because You want to keep the fractions.
People will call this angle 3 pi halves. They won't say 3 halves pi. It's just the way people say radian angles. So write it the way that people are most likely going to read it. Okay, let's split each one of these in half. That was terrible. Try again. What is that in terms of angles?
1 pi
45.
4.
45 degrees.
45.
Pi over 4.
And it's pi over 4s.
Oh,
Okay? Let's do this one.
135.
What's that?
135.
135
3 pi fourths.
or 3 pi fourths. Okay, let's do this one.
220.
220. Well, yeah, 220. No.
225.
225, you're just adding 45 to 180.
Yeah.
So 225 or
225 or
add a fourth to 1.
yeah, 4 to 1.
Add a
5
fourth to
fourths.
5 4.
5 pi fourths.
5 pi fourths. And then finally, the last one.
7 pi fourths.
First, let's do degrees.
It's just going to be
315.
315, or now in terms of radians,
So,
7 pi fourths. Good. Okay, the other angles that we commonly do on the unit circle and we get used to are increments of 30 degrees. So I'm going to mark off here, maybe I'll write this one in further. This will be the 30 degrees,
60.
60 degrees, what will this one be?
120.
120. What will this one be?
150.
150. What will this one be?
210.
210.
240.
240.
300.
300.
330.
And 330. Okay, now let's do it in radians. 30 degrees in radians. This is 1/12 the circle.
Yep. That's next.
So pi over 6. All right, 60 degrees
It's going to be
is 1/6 the circle.
Pi.
2 pi 6.
2 pi 6.
Which is the same thing as pi thirds. But yeah, just add pi 6.
Oh.
You got the right idea. Okay, going over here, 120 is the same thing as
2 pi.
5 pi 6.
2.
no, not 5 pi 6.
Pi.
It's not 4 either.
Wait, now let me.
Wait. Yeah, it is 4 pi 6.
4 pi 6 or 2 pi thirds.
2 pi 6.
2 pi thirds. What's this one?
4
It's
pi 6.
4. 5 pi 6.
2 pi.
5 pi 6.
No.
This was 4 pi 6.
Oh, thank you. And the next one's 6 pi 6.
6 pi 6 or pi. Now we got 7 pi 6 for this one.
And then the next one's going to be 8 pi 6.
7 pi 6.
8 pi
This
6.
one's 8 pi 6, which is the same thing as 3,
It's 2.
or
3
4
halves.
pi thirds, sorry. 4 pi thirds. All right, this one is
7 pi 6, 8 pi 6, 9, 10 pi 6, which is the same thing as 5 thirds.
5 pi thirds,
And then after that is 11 pi 6.
11 pi 6. Good. Okay, so that's doing it in radians. Good?
Yeah.
Okay, so we're going to come back and we're going to finish filling out the unit circle, filling out the coordinates. But before we do that, one more thing geometry-wise that we need to cover, the last theorem of this chapter. The last theorem of this chapter that we need to cover is actually a really cool theorem. Here's the way it works. Take a circle and inscribe in the circle any angle you want. So in other words, pick any 3 random points on the circle so that we inscribe an angle. So here's an angle with some measure theta, whatever.
Okay.
Now make a central angle using these same 2 points.
Oh, what?
A central angle,
Okay.
so it uses the origin. Make a central angle, and it ends at the same 2 points that this angle did.
Okay.
This will always be exactly 2 theta. It will always be exactly twice as big.
That's so cool.
It is cool. Very surprising, not at all intuitive. That's what we're going to prove.
It's called theta or theta?
Theta.
Theta.
TH.
Last top beta. Beta's a B.
Alpha, beta, gamma, theta, and phi will be the often Greek letters that we use to.
What was the last one?
Phi.
D.
T-H-I. Phi. Will be the common letters that we use to represent angles. Anyways, so that's what we're proving. Okay, so first we're going to prove a special case of this. So first I'm going to prove the special case. I've got some central angle, or I've got some angle, but I'm going to assume it goes through the origin. So let's start by handling the case where it goes through the origin. So here's A, here's B, here's theta. I'm trying to prove that this central angle is equal to 2 theta. You with me?
There's two of that, right there.
Yeah, I'm trying to prove that this angle is twice as big as that. So far I know that this is equal to theta. I'm trying to argue this is 2 theta. How am I going to make that argument? First off, look very carefully at this triangle over. What?
Make a triangle between A and B.
We don't really need that one, but
Do we know
I guess
that
we
A and B is a
sure.
40
Let's put it there.
is a 90-degree angle?
No, that's just arbitrary.
Actually
You're
not.
saying that that those two angles are equal, right?
No, I'm trying to prove this angle is twice as big as this angle.
Okay. So nothing's equal, right?
So we don't know what this angle is yet. I'm trying to prove it's equal to 2 theta. Okay.
Triangle, whatever that is isosceles.
The left-hand triangle is isosceles. This is the same as this, so its base angles are the same, so this is also theta. Good?
Which means that one's congruent to.
Now this one is also an isosceles triangle. So whatever this angle is, we'll call alpha, is congruent to whatever this angle is, alpha.
Right.
So triangle AB
Which means
Therefore,
is not a right triangle?
Which one?
Triangle AB is not a right triangle?
No.
Or it is?
it's not.
No, it's not a right triangle.
therefore theta and
Maybe we'll call this point over here C, so that we can talk about things.
therefore theta and alpha equal theta and alpha together make an isosceles triangle because
No.
no wait,
What are theta and alpha together?
they're
Angle A.
angle A.
No.
Angle A. What is angle A?
Angle A is CAB.
It's 90.
Huh?
It's right.
It's a right angle. How do you know that? One of our theorems is if you inscribe a triangle in half a circle,
It has to be right angle.
it has to be a right angle. Okay, perfect. So I know that theta plus alpha is equal to 90 degrees. Right?
Wait a second. What if it's like the top one where angle A.
So draw a circle, make one of the sides of the triangle the diameter of the circle. Pick a point anywhere.
Okay.
Create a triangle with that point. That angle is a right angle. That's what we proved. Doesn't matter where you pick that point.
So you're saying the top circle right there is incorrect? The top one.
The top circle, this circle?
Yes.
So this is what we're proving. I'm proving a special case first, where one of the angles happens to go through the origin.
So I'm saying. So we're gonna prove that one next.
We're working up to proving it in general. So we're going to handle 2 special cases, and then we'll have the general proof.
Okay.
So special
Right.
case 1. So we got that to right angle.
That's freaking cool. Okay.
So then I know double everything. 2 theta plus 2 alpha
Equals 180.
is equal to 180. Now notice, look at now just this triangle over here, triangle AOB. Its angle sum is 180 degrees. What are its angles? We'll call this angle right here beta for a second. Its angle sum is beta plus 2 alpha has to equal 180 degrees.
Right.
So, what do you see?
Therefore,
2 theta
Theta
is beta.
is beta. These have to be equal to each other.
Right.
yeah.
So, beta is in fact 2 theta. It's double that. That's what we were after.
Cool.
Okay, we handled one special case. Now we need to handle our 2 general cases. So one case, I shouldn't say special case, we're handling 3 cases. So we handle the case when the inscribed angle goes right through the origin.
Right.
Next, I'm going to handle the case where the inscribed angle has the origin in its interior. And then finally, I'll handle the case where it has
The origin is exterior.
in its exterior. Perfect. So those are the cases I'm handling. So next case now, we need to handle the case where we've got some inscribed angle. All I know about it is it's got the origin in its interior. So we'll call that A, we'll call that B, we'll call that C, following our convention up there. That's point O. So what are we going to do here? I'm trying to argue that this angle, I'm trying to argue that angle AOB is twice as big as ACB.
Right.
So we'll call that theta again. Trying to argue this one is equal to 2 theta. How am I going to make this argument? Here's the way it works. I'm going to not bisect, but I'm going to split this angle through the origin.
Okay.
Okay? So now, I know that this portion of the angle is twice as big as this, and I know that this portion of the angle is twice as big as this, using this twice. So let's label it. Let's call this top half of angle C, let's call this top half alpha, and this bottom half beta.
Okay.
So this angle right here, angle alpha,
It's double because
its
of the
central
90
angle is
degrees.
twice as big as it.
Right.
That's what we proved up there.
Right.
Similarly, here's an angle, and its central angle has to be 2 beta.
Why?
It's the same argument as up here. You just flip the picture down. Our angle goes through the origin. So we're talking about this angle, right?
Oh, so you just make it upside down.
Yeah.
Okay.
But it's the same argument because if we complete this triangle, here's our right angle.
Okay.
So same argument as above. So if that's alpha, that's 2 alpha. If that's beta, that's 2 beta. So if this whole thing is theta, then this whole thing is 2 theta. Good?
Yeah.
Alright, so now let's come back to our initial picture here and handle the case where the origin is outside the circle. Probably the hardest case. So, let's see if I can think how to argue this. What would happen if I took, that blue does not erase very well. Maybe I'll just draw a line since I can't do a dot line. Through there. Okay, I think I got it. So, starting with this angle, draw a line, put the line through there, and call this angle right here alpha.
Okay.
Then this angle, this one right here, has to be 2 alpha. Because it's a central angle using the same endpoints as this angle. Alpha is this angle right here.
Right.
Here's a central angle using those 2 same endpoints where
Right.
one of the sides is
Just
the
like the
diameter.
first one we did.
So that's using the first one. Okay. Now, notice that this whole thing, theta plus alpha, has a corresponding central angle. Maybe I don't really have another color. So this whole angle right here, from here to here, that's a central angle using as its endpoints this and this, which is the angle theta alpha. So this whole thing is 2 times theta plus alpha. And so now, I need to argue that this portion right here is 2 theta, and we're done.
Right.
Since I know that this whole thing, since I know that this whole thing is double this whole thing, and since I know this piece is double this piece, then this piece has to be double this piece.
Right. Yeah.
So that's how we get that this is 2 theta, as that angle. See it?
Yes.
Okay. Alright, so that ends the last theorem of the chapter. So now let's quickly introduce sine and cosine and fill out our unit circle. Okay, definition. This won't be in your book, but I want to introduce you to these strict functions. We'll introduce them again at the end of class so that we can finish filling out our unit circle. So by definition, cosine of theta, this is a function, takes an angle, it spits out the x-coordinate of that angle on the unit circle. That's what we're going to define it to be. Similarly, we're going to define sine of theta. That's a function that takes an angle and it spits out the y-coordinate on the unit circle. Let's start doing some of these. So let's look at some of these points really quick. This point on the unit circle, what's its coordinate?
1, 0.
1, 0. What's this one's coordinate?
1, 0, comma 1.
0, 1. What's this one's coordinate?
Negative 1, 0.
Negative 1, 0. What's this one's coordinate?
0, negative 1.
0, negative 1. Perfect. So now, if I were to ask you, what is the cosine of 360 degrees? What is it?
Negative
1, comma 0.
It's just 1. It gives the x coordinate.
Oh, 1.
What is the cosine at 90 degrees?
0.
0.
What is the cosine at 270 degrees?
Negative 1. No.
0.
0.
0. What is the cosine at 2 pi?
1.
1. What is the cosine at 7 pi?
There's
0.5.
Not sure where you're getting that. The x coordinate at 7 pi radians. Pi radians gets me how far? Start right here. How far does pi get me?
Way over there.
Pi radians gets me exactly halfway across the circle.
Right.
Here's pi radians. Here's 2 pi. Here's 3 pi.
Oh.
Here's 4 pi.
5
Here's
pi,
5 pi.
6 pi.
Here's 6
7
pi.
Negative 1.
Here's 7 pi. It's negative 1.
Oh.
Question. What's the cosine of 2,564 pi?
It is 1.
It is 1.
1. Because every 2 pi gets me back where I started,
Yeah.
and that's an even number. Okay, let's start with sine. What's the sine of pi halves?
It's 1. 1. 1.
Yeah.
1. What's the sine of 5 pi halves?
0.
Try again.
Negative 1.
Try again. 1. Can only be so many options, right?
Yeah.
4 pi halves gets me all the way around the circle.
Right.
5 pi halves gets me back to the top.
Yeah.
Okay. Let's try one more. What's the sine of pi?
Pi is
0.
0. Okay, I lied. I'm going to do one more. What's the sine of pi fourths?
It's fourth. Half.
No.
Yeah, 1/2.
We don't have it on our unit circle, right?
Right.
Okay, so that is what the unit circle is all about. You fill out these coordinates, and it helps you calculate the sine and cosine function at all these various points. All the points we have marked on here are the only points trig students know how to calculate the sine and cosine of.
That's it.
Yeah, they don't magically, if you went to a trig student and you says, what is the sine of pi sevens? They wouldn't know.
Which Brad did.
Because it's not a point on your unit circle. No, pi sevens isn't one of these special angles. So they only memorize it for these very special angles. So we're going to finish filling out this unit circle. We already did it once talking about homework.
So you can't find pi fourths?
Well, we're going to find it. It's the sine of pi fourths is the x coordinate here. And the cosine of pi fourths is the y coordinate there. So we're going to figure those out.
I think it's other.
I'm not sure what I said. Cosine gives us the x coordinate, sine gives us the y.
Yeah, you switch it.
Sorry. So let's figure that out. We need to figure out the coordinates of this point. I need to figure out how far over it is and how far up it is. You with me?
Yeah.
So I'm gonna drop altitude down, create a right triangle, and I'm gonna draw that triangle over here.
Okay.
So redrawing that triangle. This is a triangle. The angle here is pi fourths. You with me?
Good job.
Yeah.
Yeah. Okay.
The x is the x that we're looking for, and the y is the y that we're looking for. The x and y are the x and y coordinates here. It's how far over we go and how far up we went to get to that point.
Hold up, I have a question.
Go ahead.
So never mind. Just answering questions from 5th grade.
Okay. So,
Yeah. After teachers, we're teaching
You understand the triangle that I'm taking and sticking here.
Yeah.
Okay, question. What is the length of the hypotenuse? This is first off a right triangle because I'm dropping altitude down perfectly.
Yeah, right.
Okay. What is the hypotenuse of this triangle?
Hypotenuse is the radius.
The radius. What's the radius of the circle?
1.
1. So the hypotenuse is 1. So we know that length.
Okay.
You with me?
Yes.
Okay, one more thing. This angle is pi fourths. This angle is pi halves. What's this angle?
5/4.
Pi fourths. Because the angle sum of any triangle is pi radians.
Right.
Or 180 degrees. So that has to also be pi fourths.
Yeah, real bad.
You with me?
Yeah.
Okay. So what kind of triangle is this?
The right triangle.
It's a right triangle and it's a
Isosceles.
isosceles triangle. So x and y have to be equal to each other in this case. Which makes sense when we look at this. The x coordinate and the y coordinate look like they're the same at this point.
It should be. Right.
However far over we go, it seems like we go about the same far up to get to this point.
Right.
Okay.
Okay, so in this case it makes sense that whatever x and y are, they're equal to each other. So I'm just going to call xx. We're trying to figure out these values. Now, what does the Pythagorean theorem tell us?
A squared plus b squared equals c squared.
Right, so maybe keep this a y for a second just to help us see it. So I know that x squared plus y squared is equal to 1 squared. The length of that leg squared plus the length of that leg squared is the length of the hypotenuse squared. But I also know that x is equal to y, so I can rewrite this as x squared plus x squared is equal to 1 squared is just 1. You with me? X squared plus x squared is equal to 2x squared. Yes. But yes, it's equal to 1. Okay, divide both sides by 2, and we get that x squared is equal to 1/2. Take the square root of both sides, and we get that x is equal to the square root of 1/2, which can be written as the square root of 1 over the square root of 2. The square root of 1 is just 1, so that's 1 over the square root of 2.
Is 1.1.
Yeah, we're not going to bother writing decimal approximations. But we never like to leave square roots in the denominator. It's just a matter of convention. There's no good reason for it. So I'm going to multiply this top and bottom by square root of 2. So I'm taking a number and multiplying it by 1, which doesn't change it.
Alright, so the square root
You don't like leaving it in the denominator
Yeah, we don't like square roots in the denominator.
or in the fraction period. Like,
In the denominator. We
It's
put it in the
1
numerator.
over, now you get 2 squared over 1.
So now we get 1 times the square root of 2 is the square root of 2.
Over 1.
Square root of 2 times square root of 2 is 2. Not 1.
yeah.
Right? What do we mean by the square root of 2? We mean the number such that when you multiply it by itself, you get
Equals
2.
Right.
Okay, so it's square root of 2 over 2. So I now know that this x coordinate is square root of 2 over 2. And it has the same y coordinate, so that's root 2 over 2. So that's the coordinates of that point.
Which one? 45?
The one we just calculated at the 45.
45?
Yes,
At the pi over 4.
at the pi over 4. Good.
Pi fourths, yeah.
So now when I ask you what is the cosine of pi fourths,
It's
what is it? What's the
it's
x
square
coordinate
root
of pi
of-
fourths?
It's square root of 2 over 2.
Root 2 over 2.
Oh, root 2 over 2.
What's the sine of pi fourths?
Root 2 over 2.
Okay, let's see how clever you are. What is the cosine of 3 pi fourths?
Of 3/4.
Uh-huh.
It's 3 pi, it's 3 root over 2. No?
No.
Wait, so
You
3
threw
root
something
over
out there.
100%.
So 3 pi fourths, where's that?
It's
135.
We're talking about over here, 135, 3 pi fourths. So what is the x coordinate here?
oh, it's
Negative.
same thing. Same thing.
Negative root 2 over 2. What's the y coordinate? It's still root 2 over 2.
Right.
So the y coordinate's the same, the x coordinate flips.
Same thing
Which
with
means
the other
5
ones.
pi fourths is negative root 2 over 2 and negative root 2 over 2.
Perfect. And then finally our last point over here.
Root 2 over 2
Different
and
theorems.
negative root 2 over 2.
Like all
No,
these are
negative.
just summed up versions of theorems.
Perfect. And so there you go. You now know how to calculate the sine and cosine at all those angles as well.
Kinda. Well, yeah, yes.
Okay, now we're missing this point. Let's go back and get this point.
Okay.
So I'm going to redraw this triangle, drop an altitude down, and I'm going to redraw that triangle over here.
Well, now it's isosceles. So
It's not going to be isosceles anymore. So dropping that down, what are we going to have? We've got our right angle here. I still know the hypotenuse is 1. This angle here is
30.
30 degrees. And so this angle up here has to be
30.
no. The angle sum is 180.
5, right? No.
Oh, no, it's, angles, the
Yeah,
angle
60.
sum is 180, it's 60.
60 degrees.
Oh, no, 5 degrees.
Okay. So we've got this triangle. We're trying to calculate its y and its x. You with me?
Yep.
Okay, how are we going to do this? What I'm going to do is I'm going to reflect this triangle down. So I'm going to reconstruct the triangle right here.
Equilateral.
So you get a 360.
So this is also going to be 30 degrees. This is also going to be length y. This is also a 90-degree angle. This is also 60 degrees. You with me?
And then
And
1.
that length side is also.
And this is still 1.
Okay.
Okay, so notice, looking at the big triangle now, black and blue, what's this angle?
60.
What's this angle?
60.
What's this angle?
60.
And so this triangle is
Equilateral.
an equilateral triangle, which means that this side length is equal to,
That side. Other.
Oh.
This side length
how long is this side?
is equal to 1.
1. So I know that 2y is equal to 1, or in other words, y is equal to
Half.
1/2. So I know the y coordinate here. Still need to figure out the x coordinate, right?
That's the 30-degree angle?
Yeah, the 30-degree angle has a height of 1/2. Excuse me. Thanks. All right. So now we need to figure out this x.
That's going to be
So I'm gonna
reflected.
just looking at this triangle. We already know y is equal to 1/2, right?
Right.
Okay. So now looking at this triangle, I know that x squared plus y squared is equal to 1 squared. X squared we're still trying to figure out. Y was 1/2. What's 1/2 times 1/2?
1/4.
1/4.
Yeah.
What's 1 times 1?
1.
1. Subtract 1/4 from both sides, and I get x squared is equal to, what's 1 minus a fourth? 3/4. Now take the square root of both sides, and I get x is equal to the square root of 3 over, what's the square root of 4?
2.
2. So it's root 3 over 2.
This is the same for the rest of them.
And now, almost, we still got to do this point, right?
Right.
So if I were to drop down an altitude for that, let me draw that triangle over here. So we're over here at 60 degrees. So 60 degrees, I know my hypotenuse is 1, this is a 90-degree angle, this is 30 degrees. This is my y, this is my x. Right?
Right.
That is this triangle drawn, scaled down some, right? Notice that this triangle is the exact same as this triangle. We just flip the x's and y's around. This triangle and this triangle are the same.
So it means it's 1/2
Yeah.
root 3 over 2.
So x is equal to 1/2 and y is equal to root 3 over 2.
So
We
it's
just
a
swap
switch.
which one's the x and which one's the y.
That's tricky.
Yeah.
So this one goes over 1/2 and it goes up root 3 over 2.
Hold up. The height is 1/2.
No, the x coordinate. We went over 1/2.
Oh.
We went
okay.
up root
Yeah.
3 over 2.
Which is,
I
okay.
feel like it just collapses.
Yeah.
It's that-
Okay.
It's in that, yeah, okay.
You see that? And now we can label the rest of these points. What's this point here?
Negative 1/2.
Minus 1/2.
Oh, and
Comma 3 over
Root 3 over 2.
square root of 3 over 2.
And we can keep going around filling out all these points. And so now you know pretty much how to calculate all the ones that any trig student does. It's just these special values. And so if I were to come along and I were to ask you, okay, what is the cosine at 11 pi 6 equal?
11 pi
So that was 11 pi 6?
Yep.
It's gonna be
Oh,
So
negative 3,
It's
2.
gonna be, yeah.
comma,
No, it's gonna
1/2.
be positive.
No, negative 1.
Our x coordinate is positive.
Oh, so it's 3
Positive
root 3 over 2,
square.
comma, negative 1/2.
Root 2 square.
Minus 1/2. So what's the cosine?
Cosine.
1/2. Negative 1/2. Root 3 over 2.
Cosine.
Root 3 over 2. So the cosine of 11 pi 6 is root 3 over 2. And so if you plug that into your calculator, that's exactly what you should get. You see it?
What determines what way you go on this?
What way you go.
Yeah, so you went from there counterclockwise. Why not
It's still worse the other way.
It's the same.
Just a matter of convention.
Which the way they usually
It
go.
can go same thing.
If we decided to count angles this way,
It'd be the same, just change up the points.
then you would change up the signs on some of them. In other words, the sine of 90 degrees would be -1. Unless we also decide to call that way the positive y-axis and that way the negative y-axis.
Oh.
So some of this is just a consequence of choice. We happen to choose going to the right positive, going to the left negative. We happen to choose going up positive, going down
Every
negative.
unit circle though goes counterclockwise.
Yes, all angles, the same way that going to the, every time you do a Cartesian plane, going to the right is always positive, going to the left is negative.
Always negative.
There's nothing special built into mathematics that says that has to be the way. We just agree as human beings to talk about it that way.
Right.
Similarly, when we're talking about the measure of an angle, we agree to start here and go counterclockwise.
Right. Right.
So, just an agreement we have.
So if we went over cosine and sine, what about tan?
Okay. So just for the sake of completeness, I'm going to really quick give you the other 4 trig functions. They're all defined in terms of sine and cosine. And so if you know sine and cosine, you know the rest. The 4 big definitions in trig are understanding, first off, the definition of pi.
Okay.
Circumference
is-
over diameter.
Right.
The second big definition, understanding the definition of a radian. The radian is the angle that marks off an arc length of 1 radius. Is that not going?
It's going.
Huh.
Sorry.
Your other 2 big definitions, the definition of cosine. Cosine of theta gives you the x-coordinate of that angle on the unit circle.
Wait, what was one after pi?
So pi, radian, cosine, and sine. Those are your 4 big definitions from trig.
Okay.
You get those 4 down, you're pretty much set. If you have a thorough understanding of those 4 concepts.
Right. Radian is the radius.
It's the angle.
It's the arc length radius around the circle.
No, it's the.
You've got the right idea, but it's the angle associated with an arc length of 1 radius.
So it's not actually the arc length.
No,
It's the,
the arc,
angle
the
associated
length of
with
an
the
arc
length
is in
of
terms
arc.
of meters.
Right.
This arc would have some amount of meters.
The angle is in terms of radians.
The angle is in terms of radians.
Right.
So 1 radian is the angle associated with an arc length of 1 radius.
Right.
The same way that 1 degree is the angle associated with 1/360th of the circumference.
So if the radius was 1 meter, then the radian would be 1 meter.
No, no, no. So, yeah, let's make this super clear. The same way that if the degree was 1 here and this was 1 foot, if I went and marked off 1 foot on another circle, that's not necessarily 1 degree. On a smaller circle, 1 foot goes further. On a bigger circle, 1 foot goes less.
Right. They're proportional to the radius.
So,
The radius is 1 foot and
we have a small circle,
an inch.
we have a big circle.
Okay.
This small circle has a radius of 2 inches. This big circle has a radius of 6 inches. With me?
Okay.
Mark off 2 inches around the circle. I get you to here.
That's a
That's a
radian.
radian.
2 inches, this angle is 1 radian. Mark off 6 inches around the circle.
Yeah, that's what I'm saying.
That's
Then
one
this
radian.
will be 1 radian. So this is still 1 radian, 1 radian,
6 inches.
but this now is 6 inches.
Yeah,
If it was
that's
2
what I'm
inches, it
saying.
would
Okay,
be
I
radian.
misunderstood what you were saying.
Length of the radius.
Yes.
Okay.
1 radian always marks off an arc length of 1 radius. That can change from circle to circle. But the radian is always the same angle. That angle is congruent to that angle.
Yeah.
Okay, good. I think we're all on the same page. Okay, so just for completion, give you the other 4 trig functions. I told you these are defined in terms of sine and cosine.
Yeah.
So here's their definitions. Tangent of theta is the last big one. Tangent of theta, it is defined to be sine over cosine. Sine of theta over cosine of theta. Now, sine of theta tells you how high up you go. Cosine of theta tells you how far over you go. So it's how high up you go
Y
over
over
how
X.
far over you go.
So y over x, right?
Y over x or rise over run. Rise over run is the
Scientific way.
slope.
Slope, yeah.
So tangent of theta, intuitively, it gives you the slope. Here's its definition, but intuitively it gives you the slope. So if I draw a line with slope 1, so tangent at pi force, oh no, I got so stuck. Tangent at pi force, so that's this angle right here. Notice that that's an angle with slope 1, right? So it better come out 1. But let's just look at it strictly based off this definition. This is equal to sine of pi force over cosine of pi force. Sine of pi force is root 2 over 2. Cosine of pi force is root 2 over 2. Anything divided by itself is 1. So tangent of pi force is 1.
Okay, that's the slope of the line.
Intuitively, what tangent gives you is the slope. Here's its definition.
What's the point?
Here's its definition. Intuitively, why is it useful? Because it gives you slope. So if you've got some angle, plug it into the tangent function, and it spits out the slope. If you're building a house, and you want the house to have a slope of 5/12 or whatever it is,
Right.
you need to find the angle that gives you that slope. And so the tangent function is what does that for you.
Okay.
Interesting.
So
That-
tangent
that-
gives you slope.
The slope. That is the slope of a 45-degree angle.
So the slope of a 45-degree angle is 1.
What does that mean? What is
It's 1. It's rise. The rise. of
It's
one.
rise over run.
So when you go over 1, you go up 1?
Yes.
Okay.
If I were to ask you to plot the line, you know your equation y equals mx plus b, right?
Yes.
Yeah.
Love that.
So if we have y equals mx plus b, let's choose b to be 0. All our lines go through the origin. Keep it simple. And let's choose a slope of 1. So we have y equals x. What does that line look like?
45-degree angle. Goes over 1, up 1.
It's
Over 1,
this
up
line.
1.
Measure that angle. That angle is exactly pi force. The slope of this line is tangent of pi force.
Okay.
So what this means is if I give you some random line through the origin, I tell you that this is theta, and I say find the equation of the line, the equation is y is equal to tangent of theta, which is m, the slope, times x. Y is equal to mx. Tangent of theta gives you the slope at some angle.
So,
So if I were to ask you, what is the equation of a line that goes through the origin and has a slope of 60 degrees? You with me?
yeah.
So that would be
5/3.
y is equal to tangent at pi thirds or 60 degrees, whichever one.
5/3.
What is it? It's going to be y over x. It's going to be square root of 3 over 1.
Over 2.
Over 1.
Oh, thank you. Skipping ahead. To 1 over 2, right?
Right.
Times x. Now, when you divide by a fraction, that's the same as multiplying by its reciprocal. So,
hold up. So times 1/2, right?
times 2. Divided by 1/2 is the same thing as times 2 over 1.
Oh, yeah, okay.
Which is equal to just root 3. So y equals root 3x
No, I'm saying,
is a line with the slope of 60 degrees that goes through the origin.
wouldn't x be 1/2 though?
Sorry, no. I know you're mixing it up with the x coordinate here.
What would x be?
We're just coming up with the equation of the line.
Okay.
So I'm using y equals mx, and I just need to figure out the m. So I'm figuring out my m here. The problem was, I said, a line goes through the origin, and it has a slope of 60 degrees.
And x is a variable.
X is a variable, so here's our line, and we were just trying to figure out what m is.
Okay.
M is tangent of theta. Tangent of theta in this case is square root of 3.
Square, and then whatever x is, that's, so if x is, 3, your slope is gonna be square root of 3 times 3, correct?
No, this is how you would plot the line now. This is the equation of your line. Y equals mx. So if you plot those points, you will plot out a line whose angle is 60 degrees. So in other words, if we were to plot out this thing, it's not going to come out nicely. Do you have a calculator on you so we can get some numeric approximation?
You want scientific or graphic?
Doesn't matter. Just you need to be able to calculate square root of 3 over and over again. Or
Okay.
something. Okay, so let's plot this really quick. When x is 0, what's y?
Y is 0.
0. So it goes through the origin. We'll mark off some points.
Yeah, that's what I'm saying, so when x is 3, y is,
So when x is 1, y is square root of 3. What does that come out to approximately? Like 1.8 something?
What, the square root of 3?
Yeah,
1.73.
1.73. So when x is 1, y is 1.73. Let's go all the way to when x is 3.
3 times.
Plug 3 in that. Yeah, it's going to be 5 point what?
Square root of 3 times 3. Close parentheses. It's 5.1.
5.1.
96.
96.
Roughly.
Anyways, keep plugging in x's and we calculate y's. And we plot all those points. That's going to give us a line
okay.
through the origin
Yeah,
whose
so that's
slope,
what I was asking.
whose angle is 60 degrees. Okay.
Right, but every time you go over, the slope is rise or run.
Right. Every time
You go over 1.
we go over 1, we go up square root of 3.
Right.
Go over 1, go up square root of 3.
Okay, I got you.
But yeah, so now you see how you can calculate the tangent at any of these angles. If I ask you for the tangent at 135, it's rise over run. So it's going to be -1.
-1 slope, okay.
Yeah.
Yeah, I got you now.
Let's calculate the tangent at 0 degrees. It's going to be rise over run. 0 divided by 1 is 0. So that line has no slope. So tangent of theta gives you the slope.
Okay.
So that's sine, cosine, and tangent. The other 3 trig functions are secant, cosecant, cotangent. And they're just the reciprocals of these.
The opposite.
Reciprocals.
What do you mean by that?
Cosecant of theta is equal to 1 over sine of theta. Just put the reciprocal. If sine of theta somewhere is equal to 1/2, then cosecant of theta at the same point is equal to 2.
It's run over rise instead of rise
What's the
over
word?
run?
Cosecant.
Cosecant.
Yes, so cosecant is a reciprocal of sine. Secant of theta is equal to the reciprocal of cosine. And then finally, cotangent of theta is equal to the reciprocal of the tangent of theta.
Okay, that's cool.
Oh, so you're
So
saying
they're just a
if
reciprocal.
If cosine is 1 and the what do you call that?
So if cosine was 1, then secant would also be 1.
Right. If it was 2.
If cosine was 1/2,
Then
secant would be 2.
And if it was 2, it'd be 1/2.
Well, cosine can never be 2.
Why?
It's the x-coordinate on the unit
Oh,
circle.
right. It can't be higher than 1.
Your cosine and sine functions cannot spit out numbers bigger or smaller than 1. or bigger than 1 or smaller than -1.
Right.
Because they give you the x and y coordinates on the unit circle.
Right.
You can't have an x coordinate bigger than 1, and you can't have an x coordinate more to the left than -1.
So what do you use the secants for?
Because your radius is 1.
Can't secants and
These have tons of use cases that we won't be able to go over now.
Is that?
But the point is, you can define them all. All the other trig functions can be defined in terms of sine and cosine.
Right.
You make sure you graph sine and cosine very thoroughly. Know it like the back of your hand. Then these other 4 trig functions, pretty easy to reason about.
Right.
Yeah.
Okay, go ahead.
It depends on the radius, right?
No. Cosine of
It
theta.
will never be higher than 1.
Cosine of theta is defined to be the x-coordinate of that angle on the unit circle.
Unit circle is 1.
Unit circle has a radius of 1.
So
We
can
can
the bigger
find
one
x and y
be-
coordinates on a bigger circle, so let's just think about that really quickly.
One of unit circle 2.
So let's go to a bigger circle really quick.
Okay.
So this time we're looking at a circle. This time its radius, what should we have?
2.
2. So now we got a radius of 2.
Okay.
What is this coordinate right here?
It's 2, 1. 2, 0.
2, 0.
Yeah, so it can't go higher than 1, depending on the radius.
No,
Hold on.
the unit circle, the radius is 1.
Well, hold on. Let's calculate it over here at 45 degrees.
Oh no, it's hard. It's exactly times 2.
It's just going to be double whatever it was here.
Right.
So in this case, it would be square root of 2, square root of 2. You with me?
Yeah.
Oh, yeah.
Okay. So this was, we're looking at this right triangle. Here's our R. You with me? So now I'm going to take that triangle, redraw it down here, and we're going to say, the fact that I put these right triangles in a circle, completely pointless. So I'm going to redraw the circle right here. Who needs, no point having a circle, redraw the triangle. Here's my triangle here. This is 45 degrees.
This is
This radius, or the hypotenuse is R, the radius of our circle, right?
right.
Down here, how far in the x direction do we go? In this special case, when the radius was 2, it was
1.
It was
pi.
square root of 2. But how did you get that? You took this number over here and you multiplied it by your radius.
Right.
So this was radius times the cosine of 45 degrees.
And the cosine of 45 degrees is
Cosine of 45 degrees is root 2 over 2.
2 over 2.
You took that and you multiplied it by 2, and that gave you the x-coordinate for this new point.
Whoa.
Similarly, the height of this is just
Same.
r times sine of 45 degrees. Right?
Yeah.
Now, there's nothing special about doing this at 45 degrees. Make this any angle theta and any r you can think of. There's theta, there's theta, there's theta, there's r, there's r, there's r.
So when you put your cosine into your calculator, you multiply it by the degree.
No, multiply by the radius. You plug the degrees in for your
No,
cosine.
that's what I'm saying. When you're plugging into your degrees for your cosine, you plug in degrees or radians.
A lot of calculators let you switch how you plug it in.
What you were saying is
So just test it, plug 360 in and see what you get.
what you were saying is you can't get higher than 1 and lower than -1.
From the cosine function. But r times cosine can be as big as you want. So now let's get a very concrete example of using this stuff.
And why can't you do it from cosine function? Because it's always a unit 1 circle. It's based off a unit 1 circle.
Yeah, it's defined in terms of the unit 1 circle. The unit circle.
That's why it can't be higher than 1 or lower.
So
than
cosine
1.
of theta, this part can never spit out a number bigger than 1. The whole thing can spit out a number bigger than 1 because your radius could have been 17.
Okay.
And so 17 times 1/2 is definitely bigger than 1. So here's how this comes up in general and what trigonometry is all about, the analysis of triangles. I might give you some triangle, and I might tell you, okay, this right here is 60 degrees. I might tell you that the radius of this triangle is, 20 meters. And I ask you to calculate the other two sides of the triangle.
It's doable.
Yeah, it's doable. This side of the
It's
triangle
cosine. It's cosine.
is-
What do you mean?
So this is
20.
x and this is y. In general, x is always equal to r times cosine of theta, and y is always equal to r times sine of theta.
That would have been so useful when they were trying to get us to do this.
So cosine of 60 degrees is
What now?
1/2. 1/2 times 20 is 10. So in this case, x is equal to 10 meters.
Oh, okay, I gotcha.
Similarly, y is equal to r times sine of theta. What's sine of 60 degrees?
Root 3 over 2.
Root 3 over 2, multiply that by 20, gives you 10 root 3 meters.
10, isn't it 5? Oh, no, you're right, you're right.
Okay.
I thought that was 10.
And so that's how tall that triangle would be. And so now you can quickly calculate the width and the height of any triangle. If you've got your calculator on you, this is assuming it's a right triangle. I'll just use the Pythagorean theorem to make all these calculations. But if you've got a right triangle and you know the angle, you can always calculate the height. Not always in your head, but if you have a calculator, you can always do it. So if I were to give you some other triangle, right triangle, this time I told you that the angle here is 39 degrees. And the length from here is 14.7 meters. In principle, it works the same thing. You take your calculator, you plug in cosine of 39 degrees, it gives you a number, multiply it by 14.7. And it's going to give you some number. And it's going to come out to, I have no idea, I'm making up numbers off the top of my head, 8.19 meters, or whatever it is.
Pretty dope. That's pretty.
All those tricks, then you should have took this class before they took trig.
Or they should have
Now you see,
This is so much more helpful.
Instead of trig.
Yeah.
Instead of trig.
you
Well,
see
before
why
trig.
it's crucial to understand your
Let's
basic
get
trigonometry, or your basic geometry before trig. That's
Let's
why I
get
don't
trig.
want to teach trig to students I haven't taught geometry to.
They go when they throw you in trig from what we took in 9th grade. They
That'd
throw
be
you.
awful.
They say, okay, here's cosine, sine, and tangent. This
yeah.
is what it means.
Didn't know
It
any of this
means-
stuff.
Tangent means rise over run. Okay, go do your math. And they didn't explain any of this, which would have been so much more
Right.
helpful.
This class should be instead of trig, in my opinion.
Well, that is why
Or
in,
trigs next.
in the world of sanity, geometry is a prerequisite to trigonometry.
Which supposedly.
And geometry used to be taught well. This is what we're going through. This is a high school geometry textbook. This is not some crazy advanced textbook that you couldn't expect students to grasp. If we went back to the year 1950 and took you into a geometry class, it would be very similar to what we're doing here. Instead of all these formulas, memorizing formulas, here's where you use the formulas. Instead, just try to understand what's the exact definition of pi, what's the exact definition of radian, what's the exact definition of sine, what's the exact definition of
So
cosine.
what you're saying is we just got lazier and lazier. Teachers did.
Whoa, they did it to get the test score.
Yeah, we've already briefly had this conversation. Part of it comes just out of standardized testing. Part of it comes from the fact that oftentimes people who go into math education at lower levels were never very competent in mathematics to begin with.
Because if they were, then they wouldn't be teaching.
Yeah, it's just the way it naturally falls out. So where I went to school, you either majored in math or math education. And everyone who really got math majored in math, with the exception of one girl. There's one girl who she chose to major in math education, and she really got the material. But for the most part, your people who went into math education had a much weaker grasp of the fundamentals of mathematics than the people who actually went and got a math major. The people who go and get the math majors, if they teach, it's usually at a university level. Otherwise, they go on and do other things.
Right.
It's rare that someone who has a math major goes and teaches a high school class or a junior high
What's
class.
the difference between math and math education?
A math major requires you to understand math. It's the harder one. You fell out of math into math education.
Oh, okay.
So-
So people just say, oh, I'm gonna go take math education because I don't.
So chances are the majority of your teachers that you had,
Kid out of textbook.
the majority of the teachers that you had, if you were to ask them questions like, what are the axioms of arithmetic? They'd be at a loss. They were never trained to think in terms of axiomatic systems to begin with. If you went and asked them to prove something like, 3 + 3 = 6, and actually prove it, they have no clue how to begin that proof. If you were to ask them what's the definition of the number 3, chances are they're going to be at a loss. That's not something that they ever went over.
Definition number 3 is 2 plus 1.
But taking that math education can give them the degree to go and teach.
Math education, so the difference between a math major and a math education is math majors will require you to go down to the foundations of all these fields to completely understand them. Math education won't. They'll replace those really hard classes for classes, more fluff classes, that are supposed to help you teach, but...
Well, to make it easier for you so you can make it easier for them. It's a thought.
Well, they rationalize it how they rationalize it, but...
So if you're teaching a math class and not math education, like, you're going down in the deep and just pushing.
Right, you're actually learning all the math that exists out there.
Right.
Not all the math that exists out there. You're learning the foundations of the math that high school students often come across. So a lot of getting the foundations of this comes from a course called Real Analysis. It's a notoriously difficult course. I have a brother who's an engineer. His last semester, he told me he was taking Real Analysis. I warned him, that's a big boy class. You sure? And he thought, yeah, I'm gonna do this. A month into the semester, he dropped the course. It's a tough course. It's not easy.
Real what?
It's called Real Analysis.
Real analysis.
It's deriving calculus. That's what it is. And so you're deriving a bunch of the foundations of what you often use in an algebra course. It gives you a very in-depth understanding of the real numbers. That's why it's called real analysis. It's an analysis of the real numbers. The real numbers are practically the most commonly used numbers in high school math courses. Anytime we were talking about a length in this course, we were talking about a real number. All these numbers we're listing out here, we're always talking about real numbers. And so, real analysis, it's a thorough analysis of the real numbers. Very small portion of your math education majors have taken that course. That's one example. So, I could give lots of examples. Huh?
You take that course?
Real analysis, yes. Took real analysis 2, took complex analysis.
Was it,
Complex analysis turned out to be easier than real analysis.
what was the hardest classes you took in college?
That's a tough question. Real analysis is up there. Topology is up there. Computation theory is up there. So I don't know. It'd be a toss-up between
Where'd you go?
those 3. Just Dixie State University.
We talked about this last week, and devotional,
Oh yeah, you missed devotional.
and last week.
Anyways, I think we're done with the lecture. But you guys can ask me whatever random questions you want.